All right, it is 2:45, so we're going to get started. Welcome to Neural Segmentation. My name is Chris Brown, Christopher Brown, whatever. Chris Brown is unfortunately associated with famous domestic abuser, so maybe don't use that. But right, Neural Segmentation. I work primarily, if you haven't heard me say this already, on Earth Engine's machine learning integration. Right, neural segmentation, this is as it concerns neural networks, and yeah, so I'll just go ahead and get started. So when we say segmentation, right, I feel like I need to clarify that it has a slightly different meaning in the context of neural networks as it does to oftentimes we think of segmentation in remote sensing. So the difference being when we say segmentation or a segmentation network, often that network is actually predicting something that's a regression, right? And then we're just treating that as a segmentation. So right, when we say neural segmentation, that's referring to both regression models and classification models that we're either using to segment imagery or something else. So before I get started, how many of you, so I think I recognize some of you from best practices. How many of you went to ML best practices? Okay, so like everybody. TensorFlow 1? Okay, cool. So I'm holding nothing back. We're just going to blast forward here. So to even begin to discuss sort of what the state of the art is, where sort of the community has converged on with image understanding and neural networks, we have to talk about convolutions and convolutional neural networks. If this is already something you feel like you know pretty well, sorry, but we're going to start from really basics here. So, right. To talk about how we build segmentation models, as I said, in neural networks, we're going to start with a very basic building block, right? So these, again, and just to clarify, these are neural networks that are performing the segmentation task, just to be clear. So one of these basic building blocks is something called a convolution. Probably a lot of you are familiar with a convolution, even outside of the neural networks domain. We're going to be using the interpretation that it's a similarity metric between two functions. It's defined, right, it's obviously defined on a continuous variable or pair of functions, but there's also a discrete analog, and that's really what we care about. Right, convolutions, there's also a frequency domain interpretation of a convolution. Convolutions, therefore, can also perform as filters of low pass, high pass, different types. We're not so concerned about sort of the signal processing use case of convolutions. Again, we're going to focus on convolutions as a similarity metric between two functions, right? So I'm going to repeat that a couple times. We have this nice diagram from Wikimedia Commons that's sort of illustrating this point. So our two functions here are this box function and this peak, this sawtooth. And when we've slid G, right, so this is something referred to as a kernel, up against F at all points and taken the dot product, in this case we're using an integral because it's not the discrete case, where that value is highest is where we consider those functions most similar. Right, so again, just trying to build this understanding of what it means and why we care about convolutions as feature or a similarity metric. So I've been saying, right, there's a discrete analog, and this is now, instead of using an integral, we're going to use a dot product. And so now we had f and g before, right, and we're moving g. G is being applied at all locations in f, across all locations in f, and we're going to really apply that logic directly here. So obviously we were looking at a 1D case. We can apply a 2D convolution where now these functions are defined with two independent variables. It's, as I described, it's a dot product. We start with g, and at every point we compute that dot product against that position in the input, right? And this input is a matrix. And this is very illustrative of how it works. It's actually very simple if you're not familiar with convolutions. We can think of this input, right? We're defining it as a matrix, but the very obvious interpretation is as an image, right? So this could be some band of a Landsat scene. This could be something predicted from some other process. This is a real valued input, or some valued input, right? We don't care. and we're sliding this convolution across. So this is just the basic idea, discrete convolution in 2D, but keep in mind, we still want to remember, though this is sort of a little fuzzy right now, we still want to treat it as a similarity metric, right? So we're going to pretend this discrete 2D convolution is somehow computing the similarity between positions in the input, the image, and the kernel, G, which is the smaller window. Okay, so I've said that, right? And I've said that this works in the 1D case, and it works in the 2D case, and there's a discrete analog. But let's go through a real example to help illustrate how we use a convolution as a feature detector. Okay, so G, right, that's our smaller function. That's our window. It doesn't have to be smaller, but in the discrete case, we're going to approximate it with fewer, as a smaller actual, with less data. That's what I'll say. And we're going to do the same thing that we just did in this case. We're going to take this window, and we're going to slide it across our input. Intentionally, we're using a binary image, I'll say binary matrix, binary input. And it's maybe not clear yet, but the values that we've chosen for G in this case, and we've picked these values, right? These weren't computed, were chosen very specifically. And so let's see what happens when we convolve these very specifically chosen G's and F's. Okay, so we do the same thing we saw in that diagram, and we'll notice the highest value in the output, the largest value in the output, or the value with the highest magnitude, right, depending on what we care about, was when G was centered at this position in F. Okay, so just one more time. When centered at that position in F, the largest value we got was 5 at that location. So what's interesting about that is that if we look at the shape of G, and the shape of F in that same position is they're identical. So in a way, we've defined G to be that which we're searching for in F. And then we've slid it over F, and then we got the largest activation where they were equivalent, or most similar in this case. So actually, before I go over to the next slide, this is a very basic interpretation of convolutions as feature detectors. Historically, if you've been in image understanding, image processing for a while, you've heard of patch matching. And so do what we're doing, but now make this patch huge. We're not talking about 3 by 3 matrices and kernels anymore. We're talking about the size of the thing we're looking for. We have an actual picture of a horse, and we are convolving that picture of a horse with an underlying image. And then we are assuming where that activation is highest is where there must be a horse, or we have some threshold. Obviously, this has some problems, right? Because just doing this directly with something that we want to find, it sort of necessitates that the objects in the underlying source image look like the thing in the patch, right? And not just look like, really the pixels need to be laid out like the image in the patch, right? If you have a horse facing forwards, that's not going to work anymore, right? And you might catch a dog that you're looking at from the side. So sure, small local spatial structures, pretty easily we can detect those and usually find what we're looking for. But large combinations of spatial features are hard to detect just using patch matching. And it's really ill-posed. It's not really something you can do with, by coming up with every G that you could think of and sliding it over an image. Okay, so that being said, let's kind of think back, just kind of go back to basics here. We're going to go back to our silly example where we're sliding this window around and trying to detect stuff. So right now we've talked about this 2D case, right? We're not going to go, this is the highest dimension we'll explore, but we can also do this in 3 dimensions, right? So there are different ways we can define it in 3 dimensions. For the purposes of this lecture, we're just going to talk in terms of a fixed depth, and that our convolution filter, our convolution kernel, our G, right, that also has the same depth as F. So now, when we're performing this pointwise multiplication, we're actually performing it not just in, across the 3 by 3 dimensions of G in X and Y, but also across Z. So remember, thinking about how we move this thing, you can imagine this window sliding across this 3D cube, sliding across this other volume, and we're actually at each discrete point taking that dot product with the cube against the source imagery. So I'm saying imagery, right? Because images in terms of remote sensing, or really in terms of camera imagery, don't just they're not 2-dimensional, right? There's not one plane that defines the image. Usually there's channels, right? We have red, green, and blue, infrared, whatever else that you have, right? So this is just an extension to 3 dimensions. Those of you who are neural net pros and are like, well, you're not talking about separable convolutions, I'm not going to. So yes, we could get into that, but for now, our definition will just concern the basic 3-dimensional case. Okay, so gotten that out of my system. Now let's kind of go back to the original problem we were talking about, or sort of the problem we eventually got to, which is that, yeah, we can detect small things locally, right? We can detect small features, but that's not very useful, right? We really want to detect our whole objects or whole structures, right? And this becomes a problem when we're doing just the simple patch matching. So there's the other problem is that not only do we not know what all of the, not only do we not have a kernel that's, this huge kernel that we know that we can make and pick any sort of orientation of our object in and find our object, is we have to spend the time finding all of those possible patches against which we want to match, all of those source features we want to find. And this is kind of unreasonable, right? Especially because what are we doing at this point, right? Are we taking our object and then finding an image to convolve it against at all orientations, at all colors, right? This starts to become infeasible and intractable. So one thing we could start to think about is trying to actually learn, right? Have some process, some optimization process that figures out what the thing we're looking for is, right? If we can tell it using some optimization objective, some loss function, right? Because we're talking about neural networks, whether or not it's doing a good job, we can have it actually itself minimize some function to find the values of these convolution kernels. And better yet, we don't just have to do it once, right? We can convolve once, and then we've found some subset of features. But as we all know, objects are not defined unless at a very high resolution or very low resolution by, right, they're 3x3 pixel kernels, right? We may be able to find something, right, that's in a very local neighborhood, but now we want to start putting some of these features together. So we've found, okay, a corner, we found a point. Multiple corners in a certain orientation plus a point, places where we know these exist, come together to form things like lines, or circles, or geometric shapes. Okay, now that we've formed some hierarchy of these convolutions to find shapes, now we can start to find, because remember, these convolutions are finding where this hierarchy of objects, right, exist in that part of the image. So you would expect there to be a high value where your third convolution has found perhaps your lines, your shapes, your points, all these other things. So we can now start to put lines and shapes together to get features, right? Slightly more expressive features like parts of a face. Then we can start to put these parts of a face features together to form faces, right? In this silly example here. At each stage where we're adding another feature detector, we're combining more of the features from the previous step. So we can take this idea of these hierarchical convolutions and combine it with the fact that, all right, so we want to combine them in a hierarchy to find more and more complex objects and shapes, but we also want to learn what these convolutions actually are, right? Because a convolution is differentiable, we can use it in a neural net context. And so that basic principle is what a convolutional neural net is it's a hierarchical feature detector. That's the basis for which convolutional neural nets and fully convolutional neural nets are built. That we have these hierarchical feature detectors with weights that we don't know, with kernels, right? We're calling them weights, but it's the values of these kernels that we don't know. And we have some loss function to help us learn those. So, of course, that's if that were that's the only thing in a convolutional neural net, we would be done. Oftentimes, there are other operations that we'll come back to, and will make more sense as we go here. But we do these things called pools, right? So oftentimes when we build a convolutional neural net, we really want to label the whole image. We want to say something that's broadly label it. Say this has a cat in it, this doesn't have a cat in it in this example. And so we'll actually pool features together so that we'll eventually reduce our information not so much into spatial dimensions, but into a feature description, to something called a salient description of the image. Right, what actually matters. Because we don't really care about, in these labeling cases, where something was, simply its presence is what we want to learn. So this is a convolutional neural net, and this is the original formulation, kind of like a vanilla convolutional neural net. And keep that in mind because that's going to become relevant sort of as we go forward here. Right, so before we blast off, anybody have any questions? Okay, so we've built our understanding of a convolutional neural net, and we haven't quite gotten to segmentation yet, but now let's talk about how we get to segmentation using fully convolutional neural nets. So before I go forward, I do have to mention this thing. I'm using the same diagram, but for a moment, bear with me. So many a machine learning practitioner, in my experience, has gone forward to build a segmentation algorithm and thought, I know what to do. I got this. I'm going to take a CNN, one of these guys, and I'm just going to slide it around an image, right? And I'll get a prediction for every point in the image. Done, right? I figured it out. And I'll get a prediction for every point in the image. I'll train it to recognize individual pixels. This is what I'll do, and that's how I'll do my segmentation. I recommend not doing this if this is something you wanted to do or know of somebody who is going to do it. I've known this, people have tried this enough in my experience that it's worth talking about not doing. So we'll get back to why you shouldn't do that later. But we do have to start with a diagram that's way too big, and we're going to have to break it down. But let's talk about how we go from convolutional to fully convolutional neural net. So if you look at this diagram here, the first half looks like our convolutional neural net, right? That's where we're reducing the dimensionality of the image. We are increasing the depth of the image, the amount of salient channels in that image, and usually go down to something that's 1 by 1 with a very large depth. And then we would predict a label from that. Obviously, we don't want one label. We want as many labels as there are pixels in the image. So two things need to happen to label this image. The first thing that needs to happen is we need to reproject that compressed description of the image in the center of the network, right? So you can almost imagine the first thing we need to do is reverse the process, right? So we've found relevant features in the image. We've now understand this image to contain things like, we're going to go back to our animals example, cats, dogs, this, that, and the other thing. We understand that they're in there, but we don't really know where they are. I mean, we do, right? We can describe where they are, but not in terms of pixels, right? In terms of a rich semantic description, but that's not really what we want. So we now build a neural network that kind of goes the other way. So we start where we build the semantic description, and then we reproject the parts of that semantic description that we care about into an output. So this process of reversing the feature extraction is known as decoding. And oftentimes when you see these two things together, they'll be split in the middle, and we'll call it an encoder and a decoder. Also, something I'll say you'll come across often is discussions of a deconvolution layer. Just to sort of say that that's sort of fallen out of style, and that's generally viewed to be no better than a bilinear upscale. You'll see these places where we're actually increasing the channels, or increasing the first two dimensions of our tensor here. And if you read any literature on this, the very early stuff talks about deconvolutions. And first of all, it's not an actual deconvolution, so it's misleading. And second of all, really, you'll do no better than a bilinear upscale. So if you're doing this yourself, that's just a plug. So that's the first ingredient to build a fully convolutional neural net, is to have a decoder. The second thing is why it's actually called fully, because that's not really clear, right? Why isn't it just called like a segmentation or segmentation convolutional neural net? So if we go back to this diagram here, one of the sort of fundamental building blocks you'll see in a lot of neural networks is something called a dense layer or a fully connected layer. So you can imagine, let's go back to our convolution image here. Yeah, this guy. Instead of building a convolution kernel and sliding that around an image, we could just build it as a dense network, right? We could just build it as a dense connection where we have every value in that input image connected to every value of the next step that's also in the form of a 2D image. And that maybe doesn't, it kind of makes sense, right? Of course, we run into this problem where we have weight blow up, right? So now for every pixel, where it's squared the number of pixels in the input and the output, and then, of course, if you include the channel dimension, things get really ugly, right? You get a ton of parameters, and if you were in my machine learning best practices class, that's not a great idea. So we could do that, but instead what we'll do is we first boil down that semantic description of the image, and then we use a fully connected layer. a fully connected layer is really just a layer where we take all of the outputs from the previous layer, and every one of those, we have a full matrix, so if it's an n layers of output, well, and n layers of input and n layers of output, we have n squared weights across which we're building a bipartite graph, where each of those weights is one of the edges in the graph. And those we learn. So historically, building a convolutional neural net ended with one of these bipartite graphs. And there's a real problem with that, which is that when we build such a model and we learn the weights in a model, it is now fixed, that final dimension, right? So we learned, we'll say, n times m weights when we were training this model, because our last feature in our convolution stack was 1 by 1 and had some fixed length. What happens if we increase the size of the input, right? Now that final output from the convolution stack is no longer 1 by 1, right? Or it could not be 1 by 1. Or it could be 1 by 1 if you increase it a little bit. But if you increase it a whole lot, you'll start to get 2 by 2s and 3 by 3s. And when we trained this model, we learned explicitly m by n weights. So how do we apply these m times n weights to these extra, really extra output channels, or extra output pixels, you could think of it, extra output, we'll say, stacks in the first 2 dimensions? And the answer is you can't, you don't know, right? Because you learned these as a dense network, and this was as if there was only one output pixel. So we can make a change here. I think I included an image for this. No, I didn't. All right, something like that. Well, something somewhat relevant will go later on, but probably should have also gone here. So what we can actually do is, instead of adding a dense layer as our final output, is use something called a pointwise convolution. So you can imagine, when we're building a convolution, there's no reason that filter has to be 3 by 3, right? In fact, we can make it 1 by 1. So if we make this convolution kernel 1 by 1, let me go back to my 3D cube. So if we imagine that in the first 2 dimensions, that cube was 1 by 1, but now its depth is still 3, and we'll apply the same convolution process. So what are we doing? Now we are at every point, every pixel, we are forming some, because we're using a nonlinear activation, some nonlinear combination of the channels in that image, but we're not really doing anything with any of the pixels spatially. And if we think, okay, so a pixel-wise, fully connected, nonlinear layer, but it's per pixel, that's just a 1 by 1 convolution, right? That's all it is. It's in our 3D convolution case, it's just a 1 by 1 convolution for each output that we have. So instead of ending our model with a dense layer, we'd like to be invariant to the size of our input. So that's where we get the fully convolutional name, is that the internal part of this, the internal piece of this model is no longer a dense layer. We can get away with 1 by 1 fully connected 1 by 1 convolutions of that are proxying this fully connected layer, but at every pixel of the feature layer, which is this innermost layer. So that's our second ingredient. So by using 1 by 1 convolutions mixed with this decoder, we get this fully convolutional neural net. So now instead of predicting one label, we can predict multiple labels. There is also a pretty common practice, which is where we'll have something called residual connections that go from encoder to decoder, because as you're probably aware, every time we pool, every time we average, or we take the maximum value of some small set of inputs from the previous layer in a window, we're losing spatial information, right? Maybe we have a bunch of convolutions and we're getting a better understanding of what's in that image, but we're losing the arrangement, information about the arrangement of those pixels in space. So that's why we'll usually have these residual connections. But let's talk about that for a second, right? So at every step, we're reducing the spatial dimensionality of the image. That makes sense for a convolutional neural network, right? Because the goal is to get a single label output, and we don't care where that object was in the image. In fact, we want to be invariant to where that object was in the image, or rotated, or anything like that. That information is not useful, so we do throw it out intentionally, right? When we're building a segmentation network, we don't actually want that. We really want to keep the information about where things were. Even if, right, we want to be invariant to where they, right, for how we predict them and where we actually segment the labels of the image, we still want to keep that information around somewhere, even if it's not helping the salient description, right? Like a cat over here is still a cat, but we also want to keep both pieces of information, where it was and what it is. So in essence, right, the best thing we could do is to somehow avoid pooling, avoid reducing the dimensionality of the image. And so a really good idea that was had by the authors of a paper we'll reference probably again, Deep Lab, was to, instead of pooling, replace it with a different operation. It's still a convolution, but it's a strided convolution, right? This is referred to as an Atrous convolution, excuse me, not strided, Atrous convolution, or more understandably, a dilated convolution. So now we still use, in this case, if it's 3x3 kernel, but we space out the weights, the places in the source from where we take that pointwise multiplication. And so now we're actually starting to reach out and build the output activation from features that were further from the center pixel. That being said, I feel like it's quickly worth mentioning that simply by the structure of layering convolutions on top of each other and having a hierarchy of convolutions, by default, you will pick up larger features, right? So if I convolve an image and I convolve it again, the activation of some pixel in the output is going to be a function of, and we're talking 3x3 windows, is going to be a function of pixels that are actually 2 away, not just 1. Excuse me, each 3x3 window is increasing the receptive field of that output pixel. But by the time we've gotten very deep into the network, it's fairly clear, and even sort of simply working this out on a piece of paper yourself, it becomes pretty obvious, right, that the pixel that has the most relevance to that output for any given series of convolutions are pixels that were closest to it in the input, right? And so you'll actually get this implicit sort of, we'll say, weight matrix, right? You can imagine at any layer of the neural network, of a convolutional neural net, such that the input pixels from the source at the point of wherever this convolution is, the ones closer to that pixel have a higher weight, right? They're more relevant. And that's really what we want, right? Like the most important pixel to describe what any pixel is the one that was closest to it in the input, which is, right, if you don't change the dimensions, is itself. But sometimes, right, while that's relevant, we will lose that information as we go further and further into the network, which is why we want to be able to do things like pooling in the first place. And we actually get this with Atrous convolutions. But more importantly, as I said, you don't lose that dimensionality reduction, or you don't get that dimensionality reduction. So this diagram shows at the top a standard convolutional hierarchy with pooling, right? We're reducing the channel dimensionality by 2 at every step. The bottom piece of this diagram shows the same thing, but with Atrous convolutions. And you'll notice that the input size of that feature map, that final output layer, isn't actually a 256th of the input. It's only a 16th. So the question might be, why don't we do this with exclusively Atrous convolutions? Ideally, we would, right? And we would lose no dimensionality. We would lose none of our spatial dimensions. Kind of a problem, though, is that we actually, this isn't just theory, we want to put it into practice, right? And by the time you're getting to the innermost layer of your, we'll say, Deep Lab v3, right? We're going to keep citing this model here. You've now got a channel of depth 2048 of width 512 by 512 because we haven't actually pooled the convolution, and that's huge, right? And if you have many of those aren't going to fit on a GPU. And you will have many of those because you're using stochastic mini-batch gradient descent, and your batches are now a new dimension on these tensors. So now we have these 4D objects that are something like 16 by 512 by 512 by 2048, and you have a couple of them. So in practice, we usually still include some pooling simply because it's prohibitive to run this on a GPU if you were to actually, or your TPU or whatever, if you don't reduce the dimensionality. So one thing that's important here, and we talked a little bit about this in machine learning best practices, is that we can actually train these FCNNs with tile-level labels. And there's no reason that just because we don't reduce the spatial dimensionality of an FCNN, right, it's fully convolutional neural networks, that we can't also use labels as training data to build some multi-class learner or multitask learner. Unlike in a CNN, which is very difficult to reproject that output into a segmentation map, with an FCNN, we can pool, use something like a global average over the first 2 dimensions of all pixels of the output, and use that as the original CNN feature description. Add some dense layers, and essentially that's what you've done, right? You've now built a CNN out of an FCNN. And if you're using multi-class learning, now you have one head that's using an FCNN to learn tile-level labels, and the other head that's actually doing the semantic segmentation. And at this point, you've just greatly increased the amount of training data you have to build this model. So that's another really powerful thing here, right, is that we've now built a broader, more generic convolutional feature extractor. So, right, maybe one thing to even think about here is that in the best case, we would never have any pooling. And I kind of already said that on the previous slide, right? There's a theoretical fully convolutional neural net using Atrous convolution that uses exclusively Atrous convolution. That it's simply using Atrous convolution as a proxy for finding features at different scales, and that we never actually have to max pool. Though in practice, this doesn't work unless your model is fairly small or is of a reasonable size. When we were working on Project Earth, a thing that I think I've name dropped now 4 times, that also Rebecca mentioned in the keynote, we basically did this, right? We didn't actually have to reduce the dimensionality at all because the model was small enough for what we were doing, and we could just use Atrous convolutions. So, okay, that being said, and my little anecdote included, back to this thing, why don't we just take a CNN, stride it all over the image? This is a great idea. And we're not talking about these residuals or these Atrous convolutions that allows us to build accurate FCNNs. So that's actually the first problem, right? Is that because we've thrown out so much of the feature, the positional information, who knows what we're actually predicting is what we want it to be, right? Oftentimes, if you're predicting some class, there's a lot of that class at the center of the image, right? So you're losing fidelity. But more importantly, this is just ridiculously expensive, right? And the same operation can be applied with an FCNN. You're now applying the number of weights in the FCNN times the number of pixels in the source image, which is somewhat expensive, right? Depending on the size of this, it could be absolutely ridiculous. And instead, you can build something that is functionally equivalent, but that doesn't require this sort of strided sliding. Somebody asked a question yesterday at this point that like, wait, okay, so you're saying do this with an FCNN, but aren't there going to be border artifacts? And stay tuned, because we will talk about how you deal with the fact that there are now artifacts between tiles. Okay, so that's our introduction to fully convolutional neural nets. And it was at a very high level, I recognize, and there's a million and one variations that we can talk about later. But does anybody have any questions on the basics? Okay. Hopefully you'll have questions. Having a question is an important part of understanding. Right, let's talk about applying these in practice, right? That'll include some of our discussions of tile border artifacts and how we actually put these things to use in remote sensing. So,
I have a question.
Oh, I'm sorry, I didn't see you. Lights were too bright.
In the middle of the fully convolutional stack, I saw that it was almost extruded to a very tiny height and width. Right? So it looks like there is less information in that than the original image. And how are we able to make more information from that less information by deconvolving?
Yes. So the question was, if we go back to this image, keep going here, of a fully convolutional neural net, it's apparent, right, and probably sometimes it's true, it's actually not always true, that any intermediate tensor in the middle, right, probably has less information in it than we had in the original image. So the question is, how are we supposed to turn that into a segmentation map? And there's 2 answers to that question. So the first being, our segmentation map probably, and really does, have less information in it than the source image, right? We don't actually need all of that information in the original image. A lot of it we want to throw out. That's the big problem. So that's kind of the first important thing to think about here is that, right, what we're producing is simpler than what we start with. And the second point that isn't really well illustrated, which sorry I didn't include a diagram that has this, is that this is actually missing residual connections. So In the case where we're using a classic fully convolutional neural net like this, we're not using some sort of deep lab type thing where we're not reducing the dimensionality. What we'll usually have are these crossbars. So you can imagine from the 112 by 112 layers in the encoder, we actually feed forward some of that information to the decoder so that we can rebuild the spatial structure that we kind of have defined loosely in the middle. So yeah, there's actually two ways that these kind of interplay that allow us to rebuild that segmentation map. Again, sort of the modern approach is not to include so much downscaling and instead use Atrous convolutions to maintain some of those the dimensions in the first, maintain the first two dimensions. Okay. Where was I? There we go. Anybody else? Okay. So, actually I should look up. All right, good. So we've been talking a lot about building these understandably complex, parameter-heavy, expensive networks to train, but oftentimes we don't need that, right? If you were in the ML best practices class, simpler is really better, right, in terms of interpretability and cost. And oftentimes in remote sensing, our scales are much different than they are for camera imagery, right? Excuse me. Instead of something where the pixels at one end of the image matter at the other end of the image, we really have something where we're at 30 meters, and because we have rich spectral information, we can do a good job if we're detecting something like material and we don't really care about spatial structure. Even time, right? If we want to include instead of some sort of spatial structure, we can include temporal context. And so we don't need necessarily in all cases that spatial context. So what we can do is we can, well, still specify this as a fully convolutional neural net. But why would you want to, right? Like, why would you ever want to do that? So this is really more of a practical concern. This isn't really something you need to work the math out for. If I wanted to train a network to make predictions on individual pixels, what I could do is just export a bunch of individual pixel features, right? That's just band 1 was this, band 2 was that, band 3 was that, great, and then it has some output. Okay, so then when I want to make predictions over an image, I am then going to apply this neural network individually to each pixel, right? That's not very computationally practical, right? Batching, which is something we do when we predict in neural networks and when we train them, is a way to get both, is to smooth out noise when we're training and to get more predictions, faster predictions at application time. And we can do the same thing if we just have a one-by-one temporally considering network. What we can do then is build a network that's just a bunch of one-by-one convolutions, right? Because if our source network was really just going to be a bunch of fully connected layers anyway against these disparate features along one dimension, we can, as we discussed to make CNN a fully convolutional neural network, we can just treat it as a bunch of one-by-one convolutions. So a series of one-by-one convolutions, and in fact, you can even treat it as a series of one-by-one, and then if you want to do some sort of temporal convolution, 1 by 3, right? Modern neural net frameworks like TensorFlow, PyTorch, and all that support 3D convolutions. So you can build a network that'll actually interpret your one-by-one data, but a lot faster than doing it individually. So now at prediction time, you're predicting entire tiles of data instead of just individual pixels applied with a neural net, disparately. So another thing to consider in practice is edge artifacts. So because we aren't sliding a CNN at every location in the image, we're going to have this situation where we have edge artifacts. And it's worth talking about for a second why we'll have edge artifacts in the first place. So we can imagine if we have some input, right, to a fully convolutional neural net. Imagine any of these tiles receiving some image worth of input. If we have a green pixel in the corner, what is that? Let's say it's a land cover class, right? Land cover classifier. I don't know, is it forest? Maybe it's moss, shrub, but like this could be all sorts of other things. As it turns out, we don't have the spatial context to know what that is. Another formulation that's a little more concrete is if we look at the receptive field of that pixel from output to input, that receptive field, and remember, so the other thing you have to consider here is that we have this sort of weighting that implicitly happens with a series of convolutions. Most of those most relevant pixels are going to be zeros, right? Because it's at the very edge of the tile. So we're throwing out 3/4 of the most relevant information to try and predict this individual pixel. And in fact, it can simply happen that what we need to see to predict it isn't there. And so because of that, we get border artifacts, where we mispredict things at the edge. And this is expected. So something that we recommend, we do internally. So if you're using TF record export or you're using EE.model, both of these cases will use over-tiling. So the tiles we send to your model, or the tiles we give you to run predictions over before we re-ingest them, are larger. They're inflated. So in general, the sort of the intuition to use here is if you need, as a person, right, at least 8 pixels in 2 dimensions of that object to identify what it is, then you should make your over-tiling 8 by 8 in every dimension. And then what we'll do is once you predict those inflated tiles, we'll crop the border. We cut it off and then reassemble them. And this works incredibly well. Usually the over-tiling, especially in low-resolution imagery, doesn't have to be huge, and you can get the seamless map. And this is, again, exactly what we do with TF records and EE.model. So another thing, this is kind of related to sort of anecdotal experiments that we've done, but we also have to kind of consider how the data changes when we go from camera imagery, where a lot of these models are developed, to remote sensing imagery, right? So the first consideration, which is a really nice one, is that objects generally tend to be at the same scale, right? Because the satellite is generally at a fixed range above the Earth, we can generally assume that the objects we're looking for will appear in terms of pixel radius the same size. We don't have to do, a lot of times when you're building a convolutional neural net to understand camera imagery, you'll do stuff like Atrous spatial pyramid pooling, which is one breadcrumb. You'll do image pyramiding and train the model with these different pyramids of images to make sure it understands things at different depths and different sizes. That's not such a big issue when we're dealing with remote sensing imagery. The other nice thing is that our receptive fields are way smaller, right? So the example I like to use is if you have an image of a cat, right, and you want to segment that image of a cat, if you have the pixel at the very tip of the tail, right, you can't call that a cat unless you see the cat's face, right? That could be a dog, right? Who knows? It's a tail, right? We have to see the whole image to be able to classify that singular pixel. That's not the case in remote sensing imagery, right? We can look at a pixel, well, I should say with a caveat, unless we're looking at really large objects like atmospheric or meteorological objects, right? Then that starts to become a little bit relevant. But when we're at really low resolution, our receptive fields are way less. And experimentally, we found just by having the resolution, or so effectively the receptive field of any of our not over-tiled, not cropped pixels, that even just using tiles that were 128 by 128, which is less than most camera imagery neural networks, if that is the maximum receptive field size of any pixel, that's still plenty. And in fact, 64 by 64 was also plenty. And this was for a land cover project at 30 meters. So that is a nice property that we have with remote sensing imagery that allows us to use smaller models and less complex training procedures that try and take into account features at different scales. Okay, so we've talked a little bit about fully convolutional neural nets specifically, but there's this other problem that's kind of around with any images where your training data needs to be dense in that it's expensive, right? So if I want to collect training data to train one of these fully convolutional neural nets, I have to have somebody go in and annotate all of those pixels, right? If I just want to do a straightforward supervised training algorithm for this fully convolutional neural net, I can cheat, kind of. I can use don't care masking, something we talked about earlier, so that our annotators don't have to mark up all the pixels, but then I'm just getting less training data, right? So this isn't a great strategy. Usually what you want to do is either some sort of multitask procedure, like we described earlier, where you're building this backbone based off of existing information, either somebody's existing model or existing training data, or you can do something else. And this is referred to as autoencoding, where you don't use any annotations. This is a form of unsupervised learning. There are caveats to using this technique. which I'm probably not going to talk about here. If this is something you think you want to do, we can talk about it. Basically, it's harder to use Atrous convolutions in this case. But you can build something called an autoencoder. What you need to build an autoencoder is, well, just imagery. That's it. You don't need any annotations. What an autoencoder does is it'll take an input, and this is in terms of an image autoencoder. It'll take an image as an input and then just try and reproduce it. The tricky thing about it is instead of it just passing the image straight through, is that at the very center, we compress the amount of information this autoencoder can use to describe the image. Right, so if we start with a 256 by 256 by 3 input, the very center is going to be a vector of, say, length 20, right? And we have to use those 20 values to describe this large image. So the effect is that the autoencoder is forced to learn, I would say, the most salient features of the image, but really, more explicitly, properties such that changing them slightly have the largest impact to how the input data would fluctuate. So we're looking for big fluctuations in the input. Which features can we learn that have the largest impact? And you'll learn these in a compressed form, and this is sometimes used to denoise imagery because you're forcing it to have to throw away stuff that probably doesn't matter. But what's nice about this is if you're encoding the most salient features of an image, right, or just those that it can use that have the most impact for reconstruction, you're learning a lot of the stuff you would learn anyway with your supervised training data, right? You're learning things like, so we'll talk about, in terms of satellite reflectance imagery, you're learning that there are clouds in this image, because you have to learn that. Those are big features, right? That would, if you didn't describe them, would have a huge impact on your loss function. You're describing things like greenness, water bodies, things that have a really big impact because implicitly they just do, right, on your training data. Things where pixels would change a lot if you didn't have a description for them. So what you then do is you build an autoencoder with what's completely unsupervised, a whole bunch of training inputs. You still have to balance it, right, so that it doesn't learn how to encode a specific class too well. And then you can apply some of the transfer learning we talked about in the ML best practices course to build a segmentation model out of this. So what you've done is you've abated the need to collect a ton of dense annotations, expensive dense annotations that you would have needed to train this thing end to end. And there's all sorts of ways to do it. You can lop off the second half, add a new one that's randomly initialized, all sorts of stuff you can do. So another kind of plug I'll make, because I like making plugs, is that Earth Engine's catalog is a great place to build autoencoders from, simply because the data is so easy to get, and we have all of it, usually, for a certain collection. And so it's very easy to just take a bunch of random samples that maybe you've stratified over some very loose definition of land cover or something like that, make a million patches, train an autoencoder, and have to use a lot less data. Bringing it up again, this is what we did for Project Earth to actually get over the fact that we had a bunch of point-wise samples. So we didn't have dense annotations at all. What we ended up doing was building an autoencoder using Earth Engine data, and then transfer learning our own autoencoder using these pixel level annotations, and then using don't care masking as we discussed in the machine learning best practices course. So you can start to combine all these things together to find creative solutions to gaps in what you have available for training your model. Maybe you have some annotations but a lot of labels, right? Then you might do multitask learning. You might have no labels. Okay, well, I'm going to start with an autoencoder. So, right, we've kind of talked about a bunch of different facets of segmentation as we can do it with a neural network. Things I haven't really talked about is high-resolution imagery, right? So obviously when you have things like I want to find cars, right, you have to start working with like 1 meter or lower to do a really good job. If you want to segment these kinds of things, or you want to do bounding box extraction, we actually talked a little bit at the end of the best practices course about. This stuff is generally a lot easier because this problem is a lot more solved. And I say that because so many of the modern machine learning models are trained on camera imagery, RGB camera imagery. And we found in practice that the larger your scale, or sorry, the lower your scale is, so the higher resolution the imagery, the less transfer learning you have to do, or the less learning you really have to do. In fact, you can take something like 15 centimeter, or in fact, I think 1 meter RGB, so this is as in this works if you take 1 meter RGB imagery, right, and you send it to AutoML, Cloud's AutoML, which is a pre-baked prediction service. You'll actually be able to detect bounding boxes in overhead imagery, right, using the pre-baked models that are based on camera imagery in Cloud AutoML. That just works. So a lot of effort has been spent in this domain, so there's a lot of existing solutions, but we're still kind of uncovering things in the low resolution, high spectral domain. So yeah, that's our very sort of light overview of, of segmentation of satellite imagery using neural networks, and I open the floor to questions. Talking about resolution, or you mean features from the encoder to the decoder?
Yeah, from the encoder to the decoder.
As in, should I do it, or why does it work?
Should I do it?
Yes, so the reason that you would even do that in the first place, sorry, so I should repeat the question too. So the question was, can we talk a little bit about these residual connections we talked about, right? So when we have these networks that we'll call them vanilla FCNNs, where we are reducing the resolution of our image, we're reducing these first two dimensions. We have these things called residual connections. I refer to them as crossbars. We're connecting the encoder to the decoder. And yes, right, so some of the, I guess I didn't mention UNet here, but UNet is one of the most off-cited architectures that does exactly that. For every reduction, there's a corresponding crossbar. And every time you do something, and I think that uses max pooling, you're throwing away some of that spatial information. So this is almost entirely necessary. If I remember the UNet paper correctly, they show how it looks before they added residual, or maybe this was the original FCNN paper, I don't remember off the top of my head, but you can see the difference for when you aren't propagating forward that spatial information and when you do. In fact, I guess it's also worth mentioning, how does this relate to when we're using Atrous convolutions, right? And do we still have to do this? So the authors of the Deep Lab paper, when they are, right, they're very reducing that dimensionality of the right, they're reducing the first two dimensions by very little because they're using Atrous convolutions. But they still end up using, because of that, either stride 16 or stride 8 reduction, still using these feed-forward connections, right? In their case, they're only using one. But in general, this is a good practice if you're using anything that's going to pool things, pool 2 pixels together. Also worth mentioning that in the remote sensing use case, this is really important. In the best case scenario, we could use a model completely void of global pooling, because unlike camera imagery where there's some slop, right, where whether we label this fuzzy bit, the pixel at the end of a cat's tail, right, I keep using cats because I like them. In remote sensing imagery, sometimes you have a pixel that's defining a whole object that is 30 meters by 30 meters, and it's really critical that you identify this object. So anything you can do to maintain that spatial structure of the source input is really important, at least in my experience for remote sensing imagery.
These models you talked about for the transfer learning, is something you guys can provide, so we have some starting points.
Yes, so the question is, can Google provide models, some sort of models from which to transfer learn of public satellite imagery or low resolution satellite imagery? I think we totally could, and we hear you guys. That is not the first time someone has asked me that. This is something we're interested in doing. I'll just throw this out there. We did, so some of like the EE.model AI platform stuff, part of the process is making it not just easier for you guys, but easier for us to be able to make these things. And this puts us in a really nice place to start putting a little more effort into things like actual ML, either data products or models, and things in this case. So I hear you.
Do we get to see Project Earth soon?
Hopefully you'll see, yes, you will see, I'll say you'll see something. May or may not be called Project Earth. I know it's not a satisfying answer at all. But yes, so actually, let me actually speak to that a little bit more. So we are entirely interested in releasing or building a more usable global land cover map, right? The sort of the dream, the white whale, is to have for every, say something like Sentinel scene as a corresponding land cover, right, map that's paired with that. That really removes so many stages of sort of the analysis process when trying to make sense and make satellite imagery usable. I think Earth Engine's gone a long way with doing things like mosaicing and reducing and access to imagery to do that, but there's that sort of last mile. So yes, this is also, I know, another unsatisfying answer, something that we are interested in trying to make public. Okay, we have 5 minutes left, so if there are no more questions, you guys can do whatever. Thanks a lot.